In this section, we're going to continue solving rational equations, but in particular, the type that we're looking at today involve what we call proportions. So a proportion is a statement, an equation, indicating that two ratios are equal. And ratios is the quotient of two quantities. So in algebra, we usually write those as fractions. So here's an example of just a generic proportion, A over B equals C over D. And of course, this doesn't mean that A is equal to C and B is equal to D. It means that when we divide these numbers, we get the same result. So for example, like a real simple one that you would know is true, 4 over 8 is equal to 1 over 2, correct? Or you can find all sorts of different ratios that reduce to 1/2, so you could come up with all sorts of different proportions that are true there. Well, it turns out solving a proportion is actually easier than most of the equations that we have been solving this far in this chapter. Because if we clear denominators here by multiplying times the LCD, which is B times D, so multiply both sides by the same number, notice we get the equivalent equation A times D equals C times B, or B times C. And so what some people like to say is to cross multiply. And that's like a little shortcut for the result we're going to get if we clear denominators. And cross multiply means to take the numerator over here times the denominator over here and set that equal to the numerator over here times the denominator over here. That will work because if you clear the denominators, that's the result you're going to always get. So that's the way that I like to do it, but you can, like in this first proportion, if you want to say LCD is 10x and multiply both sides by 10x, that's perfectly fine. But it's really quick and easy if we just cross multiply. 9 times 2, so this implies the following: 9 times 2 is 18, is equal to 5x times 3, which is 15x. So divide both sides by 15. X is 18 over 15. And that does reduce. Both of those are divisible by 3, so we'll reduce that. 3 goes into 18 6 times and into 15 5 times. So x is 6/5. And if you want to check that, we won't check most of these, but let's do this first one. You got 9 over 5 times 6/5. Does that reduce to 3/2? Well, the 5's here would cancel, and we've got 9 6. That does equal 3/2, so that's a true proportion then. Sorry, that's a little bit off the screen there. Alright, so let's go on to the next one. Here, x plus 1 over x plus 2 is 7/3. So we can cross multiply again. 3 times x plus 1. The thing we need to be careful about here is making sure we're going to distribute that. Equals 7 times x plus 2. So 3x plus 3. So distribute on both sides. The 3 through the x plus 1, the 7 through the x plus 2 is 7x plus 14. Subtract 7x from both sides, we get negative 4x on the left, and subtract 3 from both sides, we'll get 11 on the right. Whoops, I'm sorry. I remember my window here. Okay, so here's what I was just saying. Subtract 7x from both sides, we get negative 4x on the left. Subtract 3 from both sides, 14 minus 3 is 11. And then divide both sides by negative 4. That implies that x is negative 11/4. No need to write that as a decimal. We can just leave it as 11/4. And of course does not simplify. Alright, so now we can see proportions are pretty simple to solve. So now we're going to solve some word problems by setting up proportions. So in this first example, we have if a 3-ounce serving of pasta contains 7 grams of protein, how many grams of protein are in a 16-ounce box of pasta? So the idea is that the ratio of the serving size to grams of protein will remain consistent. So the ratio we're looking at, like I said, is serving size to grams of protein. Now you could flip this ratio, the grams of protein, which I spelled wrong, sorry, it's EI, could be in the numerator and the serving size in the denominator. It's just when you set up your proportion. So you're going to have two, you want to find two of these fractions, set them equal to each other. That make sure you've got serving size in the top of both ratios, grams of protein in the denominator of both, or if you flip it, it's consistent across both ratios. Okay, so one pair, so you're looking for pairs of information. 3 ounces of pasta to 7 grams of protein, so 3 ounces to 7 grams, assuming each ounce contains the same number of grams, then we can translate that, say, well, that means 16 ounces should have X grams. Of course, X is the number, you can use whatever variable you want, number of grams of protein in a 16-ounce box. And I just put the labels in here just to make sure we're clear what we're talking about here, but of course we don't need the labels in there when we solve the proportion. We cross multiply, 3x equals 7 times 16, 16 times 7, 42, 11, 112. So x is 112 over 3. That doesn't divide evenly, but let's see. 37 1/3 grams of protein. Whoops, I spelled protein wrong again. In a 16-ounce box. Okay, so just using the idea that the ratios will be equal for, even if we have different serving sizes, we can find those ratios. That's what should be equal there. Okay, in the next example, it says a horticulturist found that 175 of 1,500 seedlings in an experiment did not germinate. How many seedlings to the nearest whole number must she plant next year so that only 100 seedlings of the same type do not germinate? So our assumption is that we'll have the same rate of failure to germinate. So if 175 of 1,500 do not germinate, then next year she only wants 100 that do not germinate, but then you can see she'll plant less seeds in order to get only 100. Now, of course, there's no guarantees here. We're assuming the rate is consistent. So this is just giving us an idea of how many we should plant based on this rate that we got in the first year. So 175 to 1,500 equals 100 to x, where x is the number planted next year, number of seeds. This should be seeds. They're not seedlings until they sprout, right? X equals the number of seeds she plants next year. Seeds. That's goofy. Okay, so we cross multiply. 175x equal 1,500 times 100, so tack on 2 zeros. So x is 150,000 divided by 175, and it says to round to the nearest whole number. So that's approximately 857.14. So she should plant 857 seeds next year. Okay, so again, if you want to check that, just 100 divided by 857. So that's the quotient here, but it's, you know, you can think of that as a rate. It's about 11% or 11.7% that do not germinate, and then 175 divided by 1500. So notice, because we approximated, these aren't exactly the same, but we get approximately 0.116 repeating. Well, that's exact. We get 0.116 repeating, which is approximately 11.7% as above. Did I say 11.6? It's 11.7 because of the rounding. Okay, so let's go on to the next type of problem. Here we can use proportions when we have two geometric shapes that are similar. So similar geometric shapes, basically the same shape, just different sizes. So maybe this triangle, and then I try to make this one look similar. So different sizes, but corresponding angles have the same measure in this triangle. And it doesn't have to be triangles, it can be any geometric shape. And so if this is side A, B, C, and this is X, Y, Z, then we can say that A to X, that ratio is equal to B to Y, which is equal to C to Z. And there's other proportions that we can, so excuse me, let me go back. We can take this proportion, this proportion, this proportion, all those ratios are equal. And what I was going to say is we can also, within the same triangle, set up ratios. So A to B should equal X to Y. And so on. A to C should equal X to Z. Now I'm not saying, this is not going to equal this, but that you're taking these two corresponding sides. Those ratios are also equal. Alright, so we can use that in the next example. It says a 60-foot tall tree casts a shadow of 25 feet. Alright, let me draw a picture. So we have a tree, 60 feet tall. It's casting a shadow of, well, the shadow is shorter than the tree, so that's not really a very good picture, is it? It's only a 25-foot shadow. So the sun's maybe over here, and it's casting this shadow. And this is 25 feet. At the same time, a man casts a shadow of 2.5 feet. The idea here is that well, we're making two assumptions. Let me draw the man first. First, the tree is completely vertical, the man is vertical, and then we have the ground is horizontal. The second assumption then, so that means these two angles are equal. The second assumption is that the sun is in the same place. This is at the same moment in time. And so the angle of the sun will create the same angle. That's called the angle of elevation of the sun. This angle will be equal to this angle. Even though, technically the tree and the man aren't on the same exact spot on the earth, they have to be, you know, close to each other. The sun is so far away that the difference in the angles are negligible. Okay? So they are near each other. These two angles are the same. These are the same, which means these are the same. And then we have similar triangles. So this man, that we don't know how, right, we're looking for how tall he is. Yes, we don't know how tall he is. Let x equal the height of the man. He casts a shadow that is 2.5 feet. So we can set up our proportion. 60 to x equals 25 to 2.5. Now these numbers actually divide nicely, so you may not want to cross multiply. I'm still going to just keep using that technique though, but this would be 10, of course. But 25x is equal to 60 times 2.5, 150. So x equals 6. He's 6 feet tall. Okay, and if you use the fact that this is equal to 10, it should make sense that 60 over 6 is equal to 10. Right? Let's put that in parentheses so it makes sense. So the man is 6 feet tall. So there's another example where we can use similar shape, geometric shapes. Okay, and on to our next type of problem where we get proportions. These problems are called work problems. And so in the work problems, we use the fact that the work completed, work done or work completed, equals the rate of work times the time worked. So the work done, that can be measured in any types of units. It depends, just whatever you're doing. If you're washing plates, it could be, how many plates you washed. If I'm grading tests, it could be how many tests I graded. If it's, anything at all, you're cleaning bathrooms, how many bathrooms did you clean? Whatever quantities those are, then the rate would be basically how many of those things did you do per unit time. So the number of completed tasks, let's say, per unit time. So it's a rate, which means you've got a unit in the numerator and a different unit in the denominator. And then, of course, time is going to be measured in whatever units. So the time units cancel, and the work done is, of course, what you've completed. All right. So this example, we're not solving. Sorry. I'm stumbling over my words. Let me think what I'm trying to say. We're not really solving a work problem yet. We're just kind of getting this idea of rates solidified. So it says, it takes me 3 hours to shovel my driveway. What is my rate of work? So the work done, of course, is one driveway, right? And this, of course, is the time to complete that work. So the rate, I'm asking for the rate. So notice that work is rate times time. That implies that rate is work completed over time. So the rate will equal, okay, I should go back to this. So shovel my driveway, the work done, that would equal one driveway. So one driveway is what I completed. time it takes me to do that, 3 hours. And so we would, oops, I'm sorry. I keep going off the screen on the bottom here. If I move my camera down where it's comfortable for me to write. Okay, so let me start over. So the rate, which is work over, I didn't put that in here, but work over time. So the work I did was shoveled 1 driveway, and the time it took me to do it was 3 hours. So we reduce the rate to a per unit of time. 1 unit at a time is 1 hour, so it's 1/3 of a driveway per hour. So that's the number of completed tasks I'm talking about in the rate. So it's not, oftentimes it's not even a whole thing that you did, right? I can only do 1/3 of the driveway for each hour that I work. And when I work for 3 hours, I complete the whole driveway. Okay, so this rate being per unit of time is going to be really helpful when we solve these problems. So in these problems, we usually have 2 or more people working at different rates. And you want to find out how long it's going to take them to do a job together. All right, so for example here, it says Sue and Bill own a painting business. Working alone, it takes Sue 3 hours to paint a 10 by 10 foot bedroom. It takes her husband Bill 4 hours to paint the same size bedroom. So she works at a faster rate than he does. How long will it take them to paint a 10 by 10 foot bedroom if they work together? So we can't just add up the times, but what we can add up are the rates, because the amount that he does in 1 hour plus the amount that she does in 1 hour should be equal to the total amount they can do together in 1 hour. So the rates are additive. So what I want you to notice here is, so Sue's rate plus Bill's rate should be equal to the rate of work together. Okay, and that's because you're talking about how much they're doing per unit of time. So her rate is how much she completes in 1 hour. Okay, let's do that. Plus how much, oh, I'm really tired, I'm sorry. How much Bill completes in 1 hour. Okay, so this is what his rate means, and that should equal how much they complete together in 1 hour. Oh, I am so sloppy today. Okay, so because we know how long it takes Sue to paint the room, we know her rate. If she can paint the room in 3 hours, then she does 1/3 of the room in 1 hour. 1/3 of a room per hour. Bill's rate, it takes him 4 hours to paint the same size room, so he can do 1/4 of the room per hour. That total is how long it takes them to complete the job working together. So the thing we're looking for is how long it will take them to paint if they work together. So let X equal the amount of time to paint the room working together. So if x is how long it takes them to paint the room working together, then 1 over x is how much of the room they would get accomplished in 1 hour. All right, let me, just to make sure that's clear, do a little chart. So work equals rate times time. So we've got Sue, Bill, and then together. So the work, whoops, I should have put Sue, Bill, and together out here, but the work they do is 1. For all situations, it's 1 room painted. The time is 3 hours, 4 hours, x hours, so the rate is 1/3, 1/4, 1 over x. So what I'm saying is when you add up these two rates, you should get the rate working together. So it's just telling you how much of the room they painted in 1 hour. All right, well, we can add 1/3 and 1/4, or we can clear denominators by multiplying everything by the LCD, which is 12x. And so we get 4x plus 7x equals 12. Oh, why did I say that's 3x? Because I was already adding the 4 plus 3. So 7x equals 12, which implies x is 12/7. Okay, so that's not a nice number, so let's write that as 1 5/7. And so the question is asking how long. So the 1 is 1 hour, and then times 5/7 of an hour. So let's approximate that. So that equals 1 hour and 5/7 times 60 minutes is approximately 43 minutes if we round to the nearest minute. So that's about how long it will take them to paint the room if they work together. The key thing to make this work is understanding that the rates are additive. So when you add up their separate rates, it'll equal their rate working together. Of course, the time is what we don't know there, so it's 1 over the time it would take them to work together. Then you can solve for that time. You might want to use t instead of x. I just happen to use x. All right, I think this is the last problem. This distance problem these are similar. Distance traveled equals the rate of travel times the time traveled. We've worked with problems with this uniform motion formula before. The work formula is really similar, right? We got rate times time. So in this example, it says the speed of a boat in still water is 29 miles per hour. If the boat travels 140 miles downstream in the same time that it takes to travel 92 miles upstream, find the speed of the stream. Okay, so we want to find the rate, right? And recall, so we worked with problems with current before. So going with the current, so we've got a river. So current goes this way. So let C equal the speed of the current. Then going downstream, oh, sorry. C is the speed of the current, and we need another variable here. Speed of the boat. Find the speed of the stream. Okay. And B equal the speed of the boat. All right. So just ignoring any numbers here. I'm sorry, I'm losing track of what I was trying to say. Yeah, let's just keep with what I was going to say. Ignoring any numbers here, going downstream with the current. That means with current. You travel C plus B, whoops, and going upstream against current, you travel, so you take, I should have put the boat for, it doesn't really matter because it's addition, but I want to be use the same pattern. So B, you got your speed of the boat plus the current. So the current makes you go faster. Going upstream against the current, you got your speed of the boat minus the current. So in this particular problem, we're told the speed of the boat is 29 miles per hour. So in this, we actually know this number. Okay, so this is just generic for all problems, or in general. And so in this case, it's 29 plus C. In this case, it's 29 minus C. All right, the other thing we know is that the two times are the same, but the distances are different, right? So if we can use the fact that the time traveled is the same for the two trips. So notice the time is d over r is a ratio, right? Or a rate. And so if we can come up with those two ratios and set them equal, we'll have a proportion. So the distance of the first trip divided by the rate of the first trip should equal the distance of the second trip divided by the rate of the second trip. The distances are not the same, right? But the time is the same. So T1 equals T2 implies this. So distance 1, that is going downstream. Let's say that's downstream. So it went 140 miles, and the rate downstream is 29 plus C. That should equal the distance for the second trip is 92 miles, and that time that was upstream. I'm just double checking, I didn't mix that up. You are going 29 minus C. Okay, so this is the proportion to solve. Once you have that, it should be easy to solve. We're just going to cross multiply. This implies 140 times 29 minus C equals 92 times 29 plus C. And 140 times 29 is 4,060 minus 140C, and 92 times 29, 2668 plus 92C. So 4060 minus 2668, 1392 equals 92 plus 140, 232C. I don't know why I wrote so big, I ran out of room. 1392 divided by 232 is 6. So C equals 6. So I'll write go up here. The speed of the current is 6 miles per hour. All right. Okay, so I'm sorry, I don't know, kind of messed up a little bit on that problem, or lost my train of thought anyway. If you have any questions about that, please let me know.